Hello, thank you for coming to my talk for the ACSESS 2023 event. My name is Hayden Frye, and my project is on the nonlinear dynamics of intense laser plasma interactions within the quantum regime. And so I'll start off by kind of explaining our model that we'll be using for this project. I'm using the Klien-Gordon-Maxwell system of equations. The Klien-Gordon equation is famously derived by quantizing the relativistic energy-momentum relationship. And then this is done here for this project for an electron ensemble. And then that equation is then coupled to Maxwell's equations in the form of the vector and the scalar potentials. And the full set of solutions can be represented as a vector. And it should be noted that our vector has different domains. So we have technically like the solution for the Klein-Gordon equation is on the complex plane, while the scalar and vector potentials are within real planes. And the vector potential is dependent on a plane that's dependent on our dimensional size of our problem. So in this case, we're doing two-dimensional, so the vector potential is two-dimensional. And this plasma model can be used to study the quantum regime of a few different cases. So essentially, it's used for sufficiently dense plasmas, so it's within the range of 1030 to 1034 particles on length scales that relate to a property of plasma known as the electron skin depth, which is essentially the range of motion that electrons within a plasma kind of oscillate. And this is kind of important for a few different cases. So for a really big one is with X-ray free electron laser experiments. It's kind of a new class of laser that allows us to probe matter at levels we haven't before. In other cases with astrophysics, specifically with X-rays and gamma rays produced from white dwarf cores and neutron stars. And lastly, what we're doing for this experiment is using it for a microscopic model of plasma wave field acceleration and hopefully in the future to study modulational instability. And most of this work done here is based off of this paper by Eliazon and Shepla in 2011. If you're interested at all in this kind of information, then I recommend that paper. It's a really good one. So my numerical scheme I'll be using is a combination of mole, and mole is a mimetic operator library. And essentially, we're going to be discretizing the spatial part of this problem with these operators. So in our case, it's a very convenient one because we only have the Laplacian operator that we're discretizing. So ideally, all we need is a single Laplacian operator, and then we can use that between all three equations. And another bonus to the mole library is that we're able to kind of straightforwardly extend our problem from both 1D to 2D or 3D. But for this experiment, I'm doing specifically two-dimensional, as I said before. And lastly, we have periodic boundary conditions that we're applying. So that isn't initially declared in the mole library. I had to kind of do that separately on my own. And it was somewhat of an empirical process of doing that. And it's not perfect, as I'll describe later, but there is room for improvement. And so the explicit time integration scheme we'll be using is a fourth order Runge-Kutta, and we can set the problem up as shown in equation 4, where you have our time step based off of our so-called supermatrix, where you have our Laplacian operator as a sparse matrix. So the entire thing is a sparse matrix, and then you apply that to our solution vector. That's kind of how we'd make our time steps for really any kind of explicit scheme, and then we can also probably reformulate that in a similar way for implicit schemes. And so our initial results are done in 2D. So we have our initial conditions. In this case, we're doing a superly polarized electromagnetic wave pulse. So we start with a kind of a plasma slab of constant density, and then you fire two circularly polarized electromagnetic pulses from both sides of it. And this kind of generates wave field acceleration, which is a common phenomenon studied for a new generation of compact accelerators. So our initial results were pretty decent. There were some issues, however, though. Our mimetic Laplacian, for one, with our periodic boundary conditions, had to be singular to work in precision. It wasn't completely singular, so luckily we were able to apply some diagonal preconditioning to get it to work and lower its condition number. And for future work, we can initialize, have different initial conditions to study different things like modulational instability, as mentioned before. And this can also be done for both cases in higher dimensions, so we can do a three-dimensional case as well. And that concludes my short talk here. Thank you for coming, and hopefully I'll see you at the event. Thank you.